Welcome to Around Space. I'm Kent Miller. Today we're going to be talking about the New Horizons mission to Pluto. I'm delighted to have with us Dr. Bradford Behr, astronomer and optical engineer. In 1992, he got his bachelor's in astronomy from Williams College in Massachusetts. In 2000, he got his PhD in astrophysics from Caltech. He then joined the McDonnell Observatory in Texas. In 2003, he joined the U.S. Naval Observatory here in D.C. In 2007, he joined the private sector to bring astronomical instrumentation down to Earth. Welcome to this show.
Thank you, Kent. It's great to be here.
So let's quickly review the discovery of Pluto.
Sure, and how that led to just a couple of weeks ago as we're taping the show, the very exciting flyby of the New Horizons mission past that distant world, planet or otherwise. It's definitely a world. So Pluto has been known since 1930 when it was discovered by an astronomer working out of Flagstaff, Arizona. And this was not a random discovery. They were a number of observatories were actively looking for planets out beyond those known up to the time, Uranus and Neptune. It was suspected that there were other bodies out there because of irregularities in the orbits of the known planets.
Right. The outer planet Neptune would sometimes arrive ahead of schedule or behind schedule, so one thought there must be additional
Something
gravitational
else,
pull.
right, pulling on it, distorting its orbit.
Yeah.
Ironically, as it turned out, Pluto was much too small to provide the amount of distortion. I think it turned out that there were some miscalculations, but for better or for worse, I mean, regardless, this at the time ninth planet was out there at the outskirts of the solar system.
Okay. Now these early photographs is just a point of light.
Exactly, and even more recently with the Hubble Space Telescope, it's still just a almost featureless blob. We'll get to that shortly. So for the longest time, all we knew was there was something out there that was a certain brightness. Exactly how big it was or how massive it was, no one really had any way of telling. In 1978, an astronomer at the U.S. Naval Observatory, rah-rah USNO, noticed a little bulge on the side of Pluto, which changed position in a regular pattern, and that then turned out to be this large moon of Pluto called Charon or Charon, depending on whether you're an astronomer or a Greek classicist.
Okay.
The fellow who discovered it, his wife's name was Charlene, so he adopted the pronunciation Charon, and most astronomers use that pronunciation.
Sounds good to me.
We did, even fairly early on, know that Pluto had an atmosphere, and not by seeing it directly, but by looking at a star that Pluto happened to pass right in front of, a so-called stellar occultation.
Right.
And instead of just blinking out very abruptly, as you'd expect from the sharp edge of an airless planet or other body, there were a few seconds where it got dimmer and dimmer and dimmer before completely disappearing.
So the extinction of the light signal was gradual.
Right. It was still pretty fast as Pluto was moving in front of the star, but not a sharp edge, indicating that there was something that was getting thicker and thicker, denser and denser as this occultation took place.
Right.
But that was about all we knew until just 20 years ago.
That moving bulge, I guess, 6 day. So we know that
so they were able
to
measure how long it took for the moon to go around, about 6 days, and I think even at that point, even though we couldn't measure it directly, we had a pretty good idea that something that close in meant that the two bodies were tidally locked to each other, that they had pulled on each other with their mutual gravity so that they always had the same face facing each other.
That'd be a reasonable guess.
Right.
Yeah.
But it was, aside from that, it was really pretty much terra incognita.
All right.
Which then, of course, got a lot of people very excited about the possibility of sending a space probe to take
Well,
a
let's
closer
first
look.
talk about Hubble, because
Yes.
Hubble improved on this a little bit.
It did. A lot of these plans for space probes were already well underway when Hubble went online, but Hubble gave us a much sharper view, as most of our audience is aware, that one of the big advantages being up above the Earth's atmosphere is a crisper, clearer view of the heavens without the blurring effects of the Earth's atmosphere. And so instead of being a single point of light, Pluto is now a couple of pixels in size. Even with Hubble's magnificent magnification, Pluto is still so far away and so small that you could tell that there was a round object out there, but exactly how big it was very difficult to tell. And there were some very careful, clever measurements using a technique called dithering, where the Hubble was told to move ever so slightly, just a fraction of a pixel in each direction, and depending on how the light patterns changed, you could then deduce what sort of surface structure, whether there were light parts and dark parts on the surface.
It's a way of synthetically making extra pixels.
Exactly,
Right.
just like on CSI, except actually using math instead of TV magic.
Right.
And there's another technique, watching the brightness of the object as it rotates. And if there's a bright spot, you'll see it come into view. That makes the whole thing look a little brighter. And then as it disappears, it gets dimmer.
So already with Hubble, we knew the surface was mottled.
Right, that there were features, as we say, on the surface. But exactly what they were, ice patches and versus bare rock, or different kinds of ices, was anyone's guess.
Okay.
Plenty of theories, but no hard data to back it up.
So what was the big dream, the idea?
Quite a few planetary scientists said, well, we've sent probes to Mercury and Mars and Venus and the Jovian, the gas giants. Why can't we do the same for Pluto?
Go there and see.
Go there and see. And every time we've sent probes to Mercury, to Mars, just complete change in our understanding of a given planet. You can make some pretty good measurements from Earth or from Earth orbit, but to really get the best possible view, of course, you want to send down a lander, but barring that, doing a flyby gives you so much more spatial resolution, meaning ability to see fine details, and making in situ measurements of the environment surrounding the planet.
All right. So I guess the first question is, flyby or land?
Well, to get to Pluto, it's an awful far, far way away. So you have to be going pretty darn fast to get there in any reasonable amount of time. Right. The scientists and engineers who launched the program would want to still be around when it gets there. And to go there and then slow down enough to to do a landing takes a whole lot more fuel. And this whole mission is a lot bigger and more expensive. So we're able to send probes to Mars pretty readily because of aerobraking, being able to sort of skip off the atmosphere to slow down, to shed a lot of that energy. But we knew we wouldn't be able to do that at Pluto. Right. So maybe someday we'll have an orbiter or a lander, but for the time being, the best that they could possibly hope for was a high-speed flyby, a couple of hours within close range of Pluto, to take as many photos and measure as many spectra and collect as much other data as you possibly could.
And I guess that's been the tradition with the other planets. We always first did a flyby.
I believe so, yes. Yeah. The Mariner probes were the ones that went to, I think, Mercury, Venus, and Mars, and not a single probe to any more than just one of them. But, but yeah, flybys are by far the easiest technically, and a good place to start. And then once you have a good reconnaissance of the area, then you are in a much better position to send an orbiter or even a lander.
So having decided on a flyby, what instruments do we carry?
Good question. You want to,
I guess first, what science do we want to collect?
Right, and so that's where these existing observations and our existing knowledge of Pluto played a big role. You can't just go there with a whole laboratory worth of equipment. You have to be very selective.
You have to pick and choose.
Usually 3 to 6 dedicated instruments, devices which will make a particular kind of measurement. And sometimes you can be clever and fit 2 or 3 kinds of measurements into a single instrument. But the amount of weight, amount of electrical power was very, very limited. So they had to be very strategic about having just enough. It's like going camping. You want to bring just enough equipment to do what you want to do without being totally weighed down by too much stuff.
Well, I was thinking, well, in terms of observation, let's say using the electromagnetic spectrum, right? We can, well, with a good resolution picture, we can get some idea of the geology.
Absolutely. So yeah, pictures, I think, are what everyone expects out of these.
Mountains and valleys, craters, whatever.
And scientists certainly just seeing what's there, seeing the structures.
So you'd want a camera.
You'd want a camera, and in fact, they have 3 cameras and what we would recognize as cameras, because there are, as we've talked about in previous shows, the electromagnetic spectrum, the whole swath of waves of various sorts.
So there's ultraviolet.
There's ultraviolet, there's visible that we see with our eye, there's infrared, heat radiation. Beyond that are all the radio frequencies. Down below ultraviolet are gamma rays and X-rays, but that central section, what's called optical radiation, is where you can learn an awful lot, both from imaging, as you said, but also from spectroscopy.
Right.
Bouncing the light or taking the reflected sunlight off of some swath of Pluto's surface and analyzing the color pattern in very fine detail.
That would tell you the chemistry of the surface.
Right. What chemicals, what sorts of molecules or atoms are present there, because each type of material puts its own characteristic fingerprint on the light waves.
Right. Then the second grouping would be charged particles.
Yes.
Now, Pluto is still inside the solar atmosphere.
The heliosphere, it's called. The
solar wind.
Right, the domain that the sun reigns over, not just gravitationally, but the solar wind, these charged particles, protons and other ions.
There's evaporation of material from the sun.
Right, that's shooting out at extremely quickly, and it causes the aurorae here on Earth. It plays a big role in weathering the surfaces of bodies
planets.
That don't have an atmosphere to protect them. So being able to measure the solar wind, not just at Pluto, but throughout this entire 8-year, was it 8 or 9 year?
It was about 9.5 or something like that.
9.5 year cruise, not a pleasure cruise by any stretch, although scenic, but during the time it took to get from Earth, they had a slingshot past Jupiter, and then that gave them a little extra speed kick to get to Pluto in a reasonable amount of time. So measuring along the way how that solar wind changed, how it got stronger or weaker depending on what various solar storms were happening was
now, the solar wind can also slowly strip away an atmosphere of another planet. And so again, measuring the solar wind at Pluto distance would be very helpful. And perhaps if Pluto had a magnetic field, then maybe it has a magnetosphere, maybe a tail, something like that. So some instruments for that would be good.
So there were 2 separate instruments that were measuring these charged particles, one for the solar wind, one for ions, particles coming from Pluto itself.
Okay.
And then
there was a dust collector.
Right.
I guess we call it the student dust.
The student dust counter. This particular instrument was built by college students at one of the branches of University of Colorado. It was named after the little girl who gave Pluto its name way back in the 1930s. And its job was essentially to just register whenever something hit the spacecraft or hit this particular sensor on the front of the spacecraft. And the reason that's interesting is to know how particles, it's called dust, it's not like the fuzzy stuff you find under your bed, it's like, you can think of it as
tiny grain of sand.
Grain of sand and even smaller. And that pervades the solar system, and knowing how it drops off, how it clumps in various places as you make that trip out to Pluto and beyond, and particularly in the vicinity of Pluto, was also of keen interest.
I think what was interesting, the student dust collector, what I think was the one instrument that was really collecting data the whole way out. So, because we want to get an idea of the dust profile throughout the whole solar system. That was very interesting.
At least along this one track that the spacecraft was following, but you take that to be representative of the whole of the solar system in general.
Let's go back to spectroscopy, because this is your strength.
Indeed it is.
So let's talk about first the long-range camera.
So, right, there's essentially a telephoto camera and a wide field, not quite fisheye, but a close-up camera, both, and for the sake of simplicity and to make sure that nothing went wrong, you wouldn't have one camera and two different lenses that swap in and out. It makes a lot more sense to have one dedicated camera with a long lens that essentially could see things from pretty far off, or could zoom in on parts of Pluto's surface or the various moons. But then and that was essentially a black and white camera, or they call it panchromatic, meaning getting all of the colors, a huge
broad
swath
bandwidth,
of the electromagnetic spectrum at once. But then, and so that was called LORRI, L-O-R-R-I, the long range. I won't rattle off the acronym because I don't remember it, but LORRI was the telephoto lens, and then RALPH, which I don't think was an acronym, just they decided to give it a fun name, was a wider field color camera that then also had some infrared spectroscopy capability built into it, so that they could measure as you said before, the composition of whatever it was looking at, not just what its appearance was.
So let's see. We also had an ultraviolet spectrometer.
Appropriate for Ralph. Ralph was joined by Alice. I think that's a Honeymooners reference. And Alice can see in the ultraviolet, bluer than blue. Not very good spatial resolution, but really good spectral resolution. So being able to pick out details in the color pattern of whatever chemicals or ices or surface features the spacecraft was being pointed at.
Now, ultraviolet is interesting because it would suggest some kind of an energetic chemical process. Now, the flyby of Jupiter was interesting because we did see aurora in the polar regions around Jupiter. And of course, those glow in a whole spectrum.
But particularly in the ultraviolet. So the New Horizons had a dress rehearsal of sorts, although not quite the same as the true dress rehearsal a few weeks before flyby that we'll talk about later. But this close pass past Jupiter was good not just for speeding up the trip, but also for making measurements, because Jupiter's interesting, even though we've sent many probes there and know a good bit about it, but also to check and make sure that everything was working properly, that all of the instruments were calibrated. So, making measurements of aurorae or energetic processes, well, that's probably where Alice got a really good workout, but then was also used to look at the faint. We wouldn't expect any strong ultraviolet emission anywhere in the Pluto system, although you never know. As it turns out, there have been quite a few surprises. But even the faint amount of sunlight reflecting off of, say, a glacier on Pluto, by looking at the ultraviolet color patterns, you could pick up that fingerprint of various organic substances. Not to say there's life there, but carbon-based molecules and other sorts of complex molecules that show up differently in the ultraviolet band.
So we would expect, just based on the moons that we've seen around the gas giants, we would expect methane, nitrogen,
some ammonia,
possibly ammonia.
Water. Earth isn't the only place. We are the ocean planet, but there's plenty of water out there elsewhere. At the distance that Pluto is from the sun, of course, it's quite cold, and a lot of these gases are liquids or even solids of a sort.
Now we know from chemistry experiments that were done a long time ago. You remember the early debates about evolution, how did it get started? And so there was an experiment where you put certain gases into a
spark chamber
bottle,
urate.
and you have a electric arc.
Yep.
Right. And then if you run it for a few weeks, you get this brown orange scum goop, which turned out to be very interesting.
Right. A lot of somewhat unexpectedly, just taking simple molecules and zapping them will make more complex molecules and
organic
molecules,
which have an interesting spectrum that you can measure with,
and a very reddish tint to them. And measurements both with Hubble and from the ground indicated that at least some parts of Pluto's surface were looking a little red. And a lot of the Kuiper belt objects further out also showed this red characteristic. So there was a reasonable expectation that there'd be some interesting chemistry going on, even with it being so cold and so dark.
So it'd be at least a patina, a thin layer of organic substances rained out on the surface.
Right.
Yeah, so Pluto, the other red planet.
Exactly.
Okay.
So yeah, this suite of instruments was deciding what to take along on this mission was probably one of the most challenging parts of planning. And so throughout the probably late 70s and the 80s and the 90s, a lot of scientists were very keen on, hey, let's send a probe, but budgets are tight. There's a lot of other interesting stuff going on. There were, at least 3 serious proposals to NASA that started getting funded, and then funding got cut off. So the principal players who were really pushing for this mission had to have quite a bit of patience and quite a bit of political savvy in order to keep the ball rolling and to finally get a commitment to fund and launch this thing.
Now, of course, there's a mass budget too. You have to keep things light.
Yes.
So tell us about the rocket they had to put under it.
Pretty big rocket. I think it was an Atlas V with added boosters, the so-called Atlas V Heavy, in order to get this thing launched. And unlike a lot of other missions, they didn't take their time. It went directly into Earth escape velocity after clearing the Earth's atmosphere. At the time it left the Earth, it was the fastest launched probe that Earth had ever sent out.
Right.
It is not currently the speed holder. One of the 2 Voyagers, I believe, has that honor because they did multiple flybys, getting a velocity kick each time.
All right.
But to get out there in under a decade meant they really had to put the pedal to the metal. And I think within a couple of hours, it was past the orbit of the moon.
9 hours.
9 hours compared to the 3 days it took the Apollo missions to get there. So it was moving.
Yeah.
And
the slingshot from Jupiter saved like 3 years.
Jupiter kicked up the velocity, I think, from 12 kilometers per second to 16, something of that order of magnitude.
Shave off a few years.
And they almost had to skip the Jupiter pass. There was a launch window, I think, of only about 2 weeks where Jupiter and Pluto were in the right position relative to each other. And if they missed that window, then they would have had to go directly to Pluto, and it would have taken several years longer.
Yeah, yeah.
So a lot of hard work from what the scientists talked about. There were a lot of weekends and vacations skipped getting this thing ready for launch. And then, of course, once it was launched and they knew it was healthy, then you sit down and you wait.
Now that's kind of interesting because the weight is a bit of a problem. I know that the team was deliberately recruited, young people, so in their 20s and 30s, young people, so they'd be still around when the mission actually got to Pluto.
Right.
But you know how it is. An accountant will show up and say, well, if you're waiting, why can't you do something else while you're waiting?
Well, and
So
for many scientists, you
yeah.
sit there with nothing to publish. Your career,
is injured.
is severely damaged. So
Right.
so yeah, a lot of the team members had to go off and do other, I'm sure, at least in some cases, interesting projects and research. But the logistical challenges of essentially going into hibernation for a period of almost a decade before, and then coming back and being ready to, you only get one shot at the flyby.
I think the satellite sent a message once a week. I think it was something like that.
Just, hey, still here, everything's good.
Yeah. But that meant that most of the team was gone, and their heads were being filled up with other research and other projects.
Right.
And so bringing the team back together at the end, that would seem to be very difficult, because you'd have to almost maybe re-educate is not the right word, but refamiliarize, or
refresh.
Everyone have to refresh and relearn everything that'd been crowded out of their minds 10 years prior.
Exactly. So, so yeah, I recall you mentioning the dress rehearsals and the planning that they would fill up roughly about a year before.
I think a few months before the flyby, they had a dress rehearsal where they command the satellite to turn and point, and as if it were taking pictures of Pluto. But of course, Pluto is still months away.
Right.
But I think that was more for the training of the people, to make sure that everyone was ready.
Right. Knew what they were going to have to do at the right time.
Yeah.
Although, as we'll talk about shortly, to a large extent, the probe had to be pre-programmed.
Yeah. All right, we'll talk about that next time.
Sounds good.
Thank you so much. And that was Dr. Bradford Behr, astronomer and optical engineer. Thank you for joining us around space, and see you next time.